Hello, my name is Shahin Heidarian, and I'm going to present our paper entitled WSO-CAPS, Diagnosis of Lung Infection from Low and Ultra-Low Dose CT Scans using Capsule Networks and Window Setting Optimization. First of all, I'd like to say that this is a very brief presentation. I did my best to include as much detail as I could in this presentation, but for more details, you can refer to the original paper. I start with an introduction of the work and then describe our proposed method more in detail. Our goal in this study is to develop an automated framework to detect the existence of infection in a lung CT scan. Basically, CT scans are generated by cross-sectional images obtained by sending X-ray beam into the body and monitoring the signal passed through the body. CT scans provide a 3D representation of the body, which is constructed by a sequence of 2D slices. In the image below, you can see different slices for a patient. You can see that some of them have the evidence of infection, while some of them has no evidence of infection. Regarding different methods to analyze CT scans, there are two main classes, slice level and patient level. In patient level, we are dealing with all of the slices for a patient, which is basically a 3D data. In a slice level analysis, on the other hand, we only focus on 2D slices. In this study, we have focused only on slice level analysis. As another characteristic of CT scans, it's important to note that CT scans expose patients to harmful radiations with devastating effects on the body. To deal with that detrimental effect on the body, the radiologists have come up with some ideas to move from standard dose CT scans to low dose and ultra low dose imaging protocols. So the common approach to reduce the radiation is to decrease the X-ray tube current in the scanner. However, decreasing the X-ray tube current will decrease the energy of the projected beam into the body and consequently impose a high level of noise on the output image. These are some sample images acquired by standard dose and low dose imaging protocols. As you can see in the left-hand images, there's a high level of noise compared to the right-hand images. Now let's see how expert radiologists deal with this issue when trying to review a low-dose CT scan and identify infection manifestation that sometimes may be difficult to identify in a noisy image. CT scans are mainly represented in the Hounsfield unit, in which pixel intensities are commonly distributed from the HU value of the air, which is -1000, to values more than 4000. It's possible to have some values out of this interval, but they're mainly artifacts. In the CT scans, some manifestations are only visible in a specific window, depending on their tissue density. Therefore, radiologists adjust the displayed window and the image contrast using two parameters, window length and window width. And in these images, you can view different windowing parameters applied to the same slice. In this study, we embedded a window setting optimization module into the binary classifier. We detected three best window settings that can be used to analyze lung CT scans, and we modified an existing capsule network-based classifier to detect the slices with and without the evidence of infection. These infections can be caused by different diseases. And finally, we enhanced the performance of the binary classification. In this study, we have used three types of data. The first one is low and ultra low dose CT scans. It contains volumetric CT scans of 100 COVID-19 and 60 normal cases obtained in the axial view, and all the images are reconstructed by the filtered back projection method. In this study, low dose scans are acquired by the MOS value of 20, and ultra low dose images are obtained using the MOS value of 15. From the slice level point of view, there are more than 7,000 slices with the evidence of infection and around 15,000 slices without the evidence of infection. The second dataset is simulated low-dose CT scans. As we didn't have low-dose images for diseases other than COVID-19, we have simulated 16 community-acquired pneumonia cases or CAP cases based on their standard dose images. For the simulation, we used the cycle GAN model, and this dataset contains around 3,000 slices with evidence of infection and more than 5,000 slices without the evidence of infection. And finally, to further evaluate the performance of our model, we use a data set of CT scans acquired using standard dose imaging protocols. This data set contains 54 COVID-19, 60 CAP, and 60 normal cases. In this slide, you can see the pipeline of the proposed method. The CT scans and the corresponding line masks are fed into the window optimization module and then go to the stack of convolution and pooling layers. We also use two residual connections to transfer low-level features into the deeper parts of the model and reduce the risk of vanishing gradient. The output of the last convolution layer will go into the stack of 3 capsule layers. In the last layer, we have only 2 capsules, each representing 1 target class. The length of each capsule, which is calculated by the L2 norm, represents the probability that the input image belongs to the corresponding target class. Now, let me elaborate some parts of the model. The binary masks are obtained using a unit-based segmentation model, which is pre-trained on different diseases and fine-tuned on the COVID-19 CT scans. For the WSO module, I will explain the module and the implementation more in detail in the next slices. So commonly, there are 2 types of windowing functions, linear and sigmoid. As can be seen in the 2 graphs, a windowing function is in fact a mapping function that changes the value in the Hounsfield unit into another interval. Here it's from 0 to u or epsilon to u, and u is set to 1 in this study. We can find the equation of this mapping function, like the equations provided here. And we can see that in both functions, we have a linear transformation, a wx plus b, and then a function which can be a min-max or a sigmoid. After finding the optimal w and b, we can trace back the values to find the optimal window length and window width values using these 2 equations. I would also like to mention that to deal with the unbalanced data set that we are working with, we have balanced the loss function using this equation provided here to penalize the errors from the minority group more than the other group. More specifically, we multiply the loss values for each class to a coefficient to balance the final loss value. To implement the WSO module, as seen in these equations, we are dealing with linear transformations. and activation functions. This can be easily implemented by a one-by-one convolutional layer with a stride 1, following by a ReLU or sigmoid activation function. And at the end, we will multiply the output by the U, which is 1 in this study. In the experiments, we set the initial values of the windowing parameters to -500 and 1400, which are standard values for long CT scans. In these tables, we can see the performance of the classifier on the test cases. In the first table, you can see that the WSO-CAPS using sigmoid window function achieves the best accuracy. And we can also see that the results after adding the WSO-CAPS, after adding the WSO module, is higher than the same capsule network without using this module. And we also investigated the result of the best model, which is sigmoid 1, when the long segmentation is not used. The results show that using long segmentation can improve the overall performance. In another experiment, we investigated various numbers of windowing channels and branches. By channel, I mean we can, instead of one convolutional channel, we can use 3 channels to find 3 window parameters at the same time. By branches, I mean that we can create some branches of the model, each with 1 window channel, and then combine the feature maps to find the final output. We used the sigmoid WSO-CAPS in this experiment as the best model. We saw that using 3 channels, we can achieve the highest accuracy and sensitivity. We also increased the number of channels and branches to 5 or more, but couldn't see any further improvement. We also trained and evaluated the best model, which is sigmoid model using 3 channels, over a standard dose CT scans. You can see the result in this table, which show the superiority of the proposed model over the same model without using the WSO module. As the last part of the results section, it's good to take a look at the optimal window setting parameters obtained by the WSO module. The model using only 1 channel achieves the window length of -555 and window width of 1032, which is quite similar to the standard window. And using the 3 channels, as can also be seen in this figure, we have 2 channels, channel 1 and channel 3, which are quite close to each other, but with different contrast levels, and channel 2, which focuses more on the main components in the lung, such as blood vessels. And this window discards the noises and artifacts as well. As a conclusion, we developed a binary classifier to identify slices demonstrating infection from low and ultra-low dose CT scans. We enhanced the classification performance by adding shortcut connections and window setting optimization module. We detected 3 optimal window settings to identify lung infections. And we showed that the proposed model have a high potential to be incorporated in other models related to CT scans to improve the overall performance and limit the process on a small subset of candidate slices or ROIs. Finally, these are the references that I used to create this presentation, and thank you very much for your attention.